Good day, we're going to talk about the CE emitter bias configuration, AC analysis where we apply the RE model to the configuration. So the emitter bias configuration, unbypassed, meaning the emitter terminal does not have any capacitor bypass to the resistor RE. So like in our discussion for the fixed bias configuration, we're going to apply the AC analysis where the DC sources will be grounded and all the capacitors will be shorted, and then after that we apply the RE model where we can solve the parameters input impedance, output impedance, and the voltage gain. So first step is to ground all DC sources and then short all capacitors. So by shorting all capacitor and then grounding the DC sources, so then after that we will substitute the RE model to the transistor, so it will look like this one. So this is the RB, so this will be the RE model. Wrong drawing. So let's draw again. So RB, so this will be beta RE. And then the current source, this will be beta IB. So small letter B, meaning this is in the AC analysis. So this is the RE model. So since I emitter resistor, so we're gonna put RE in this terminal where ang kaning RB connected siya sa ground. And then RC, so since naka-ground ng VCC, so this will be ang RC. One side of the RC will be connected to the ground. So in the RE model, as you can see na ay R sub O. There's an R sub O, where in this topic, when we're going to neglect R sub O, since if you include this parameter in the model, so it will complicate all the formulas, no? So to make it more simpler, let's neglect the R sub O, where this will be I sub IB. This is the input current sub I, input impedance ZI, this is a BI, this is collector base. So small letter designates AC analysis, no? So kung capital letter na siya, that is DC. Output impedance, and then the output current I sub O. So this is currently is I sub E. So this is the RE model of the common emitter bias configuration. Well, as you can see, ang kaning RE model, this is being substituted to this transistor, no? So since now there's an emitter resistor, so that's why it look like this one. And then we've neglected the R sub O since we want the discussion to be more simpler. So this is the RE model. So like the fixed bias configuration, we're going to calculate the input impedance, output, and the voltage gain out of this equivalent circuit. So in this computation, so the input impedance is seen to this, this G sub I. So we need to calculate the equivalent resistance of beta RE and R sub E, and then iparallel na to sa R sub B in order to calculate the input impedance. So this will be result. No? So if you look at the input voltage here, so since parallel naman sila, so the voltage, input voltage across R sub B and the input voltage across beta RE and R sub E plus R sub E are equal since parallel naman sila. So therefore VI is equal to I sub B times beta RE plus I sub E times RE. So that will be that will be the result. So that one. So therefore in our previous discussion, as you can see, I sub E is just equal to beta plus 1 IB, diba? Formula sa electronics 1. So therefore by the way, so this will be kanina na siya, no? Na just na sobrahan ang parenthesis. So therefore substitute this one here. So therefore VI is equal to I sub B beta RE plus beta 1 times IB R sub E. So as you can see, beta plus 1, quick recap, no? Beta plus 1, ang range niya is 50 to 400. So if you look at these values 50 to 400, if you compare that to 1 is very very small number, no? So therefore we can neglect 1. So therefore this will be IB beta RE plus beta IB RE. So let's continue this. So let's copy this. This will be BI is equal to IB beta RE plus beta IB R sub E. So common ng IB, factor out IB times beta RE plus beta capital R sub E. So VI divided by IB is equal to, as you can see, VI divided by IB is just equal to, so pwede natin na siya equal to, so let's name this one ZB. So therefore this will be equal to ZB equal to beta RE plus, so common ang beta, so factor out beta RE plus capital R sub E equal to ZB. So as you can see, ZB is equal to beta quantity R sub small letter E plus capital R sub E. And then in order to calculate the input impedance, is just equal to RB parallel siya sa ZB. So RB parallel ZB. So this is how you calculate the input impedance. Memorize the formula, beta R times R sub E plus capital R sub E. And then parallel siya sa RB. So you can calculate the input impedance. So the output impedance is very easy, no? So since there's no R sub O, so therefore the output impedance is just equal to R sub C. No? So let's now compute the voltage gain AB. So the voltage gain is equal to V over VI. No? Where VI So where voltage gain is equal to V over Vi. So from this circuit diagram, equivalent circuit, where as you can see, Vi is just equal to by the way, this is IB is equal to Vi divided by ZB. So, and also on the other side, the output side, V out is equal to, so since in the different direction ang output, so I out, negative I out times RC, where the I out current is just equal to beta IB, so therefore this will be negative beta IB times RC. Substitute na to ni dili, and also VI dili. By the way, VI is equal to kumpleto sa bali sa ZB, so beta R sub E plus capital R sub E. Substitute this one dili, and also the so voltage gain is equal to V is negative beta IB times RC divided by, so multiply, so therefore this is IB beta R sub B plus. So cancel lang yung cancel ni. So cancel this one. So therefore voltage gain is equal to negative RC divided by small re plus capital R sub E. So this is the voltage gain. It's the voltage gain. So therefore the important parameters are formulas. GA is equal to ZB parallel RB, where ZB is equal to beta times R sub E plus capital R sub E. Z out is equal to RC, and then the voltage gain is negative RC divided by. So these are the formulas for the unbypassed common emitter bias configuration. So let's have an example. For the network, so without the capacitor CE, unbypassed, determine the R sub E, input impedance, output, and the voltage gain. So as you can see, natay capacitor unbypassed, meaning the capacitor CE is not connected to the emitter terminal. And then later on we'll compare if what's the voltage gain or the input impedance if we connect the collector, the capacitor, emitter. We'll compare. So let's start with letter A. So solve. So the formula na. So R sub E is formula is 26 millivolts divided by capital I sub E, meaning the DC equivalent of the emitter current. So in order to calculate I sub E, solve sa nato ang IB by base emitter loop. So therefore 20 minus IB capital 470K plus minus 0.7 minus I sub E times 0.56 kilo ohms equal to 0. So we're gonna calculate I sub E where ang formula, diba, I sub E is equal to beta plus 1 times IB. So in terms of IB, so this will be IE is equal to divided by beta plus 1. Substitute the ring equation, 20 minus I sub E What is beta? 120, so therefore 121 times 470k minus 0.7 plus IE 0.56 kilo ohms equal to 0. So common ang I sub E, so balhin nato ning duha sa pikas. So therefore this will be I sub E times 470k divided by 1P1 plus 0.56 kilo ohms equal to 20 minus 0.7. So solving for I sub E, this is 20 minus 0.7 divided by 470k divide 1 to 1 plus 0.56 kilo ohms. So use your calculator. So therefore answer is 4.34 milliamps. So I sub E is equal to 4.34 milliamps. So R sub E is equal to 26 millivolts divided by milliamps. So R sub E is nasa 5.99 ohms. So muna to so that's our R sub E. So letter B, input impedance. So input impedance from our calculated formula, derived formula, is equal to ZB parallel R sub B. So ZB to beta times capital R sub E, emitter resistance, and so this is 120 times 0.56k plus 5.99. So ZB is equal to 120 times 0.56 plus 5.99. This is equal to 67.92 kilo ohms. So ZI is equal to 67.92 kilo ohms parallel with 470k. DI is equal to parallel 1 over 1 plus 470k. So if it is parallel, so the smaller the value, the answer of this, it should be closer to the smaller value. So which is equal to 59 ohms. So if you parallel to resistors, resistances, if the equivalent resistance will be equal or almost equal to the smaller one. So if your answer is 1, if it is closer to 470k, expect your answer is wrong. It should be closer to the smaller value, ZI. So ZO, it's very easy, ZO is just equal to 2.2 kilo ohms. And then the voltage gain is equal to negative RC, R sub E parallel. This is negative 2.2k divided by 0.56k. That's 5.99. Voltage gain is, so don't forget the negative, divide so this is negative 3.88. So that is no unit. This is unitless. Unitless na siya because it is just a gain, V over VI. So our input impedance is equal to 59.34. So output is 2.2K. Voltage gain is negative 3.88. So what if we connect the collector, the capacitor, emitter capacitor ng CE? So what do you think will happen to the input impedance and the voltage gain? So let's redraw the circuit. So what will happen, what do you think will happen if we connect the capacitor to the emitter terminal? So like what we discussed earlier, in order to analyze the configuration in AC analysis, the first step you should do is to ground all DC sources and short all capacitor. So if you ground this one, RB and RC will be connected to ground. This capacitor will be shorted, this will be shorted, and also this will be shorted. So what do you think will happen to 0.56 if this capacitor will be shorted? So if you short this one, this capacitor will be neglected, no? So mawala na siya. So it will be mahimo siya. So it will be equal to a fixed bias. Mahimo siya. Let's draw the array model. So ground this one, short all capacitor. So this will be grounded, connected to the ground for 70K, and then this is beta RE. So since shorted ni siya, so this capacitor will be eliminated or neglected, no? Since ma-short ni siya, so the equivalent resistance will be equal to 0. So since the majority of the current will not flow to the resistor, but it will flow to directly to the ground. So therefore ground is here, and this will be grounded, and then the current source is beta IB, and then this will be equal to RC. B out, output C out. This is ZI, VI. This is IB. This is I out. This is I sub I. So as you can see, if there's a capacitor, so this is a bypass capacitor, no? The RE model of a common emitter configuration is the same with the fixed bias na RE model. Since the emitter resistor will be equivalent to 0 since na short maning capacitor. So all of the formulas na with the fixed bias configuration in the AC analysis, you can apply those formulas to the bypass emitter configuration. So the formulas will be GI is equal to RB beta RE, output is equal to RC, and the voltage gain is equal to negative RC over RE. So let's compare. So since we've calculated the RE, so we have the same RE. So since we have the same I sub E, in our formula, so in this circuit, ang RE niya is equal to 5.99. So therefore, this is equal to 5.99 ohms. So since in DC analysis, the same ang tumakompute sa emitter current, which is 4.34. So if the same emitter current, the same R sub E, but ang formula sa AC analysis ay lahi. So therefore, this is CI is equal to 470k parallel with 120 times 5.99. So input impedance is 1/470k plus 1/120 times. So this is equal to 717.7 ohms. Muna ang equivalent resistance. So for ZO, this is equal to 2.2k. And then for voltage gain, this is negative 2.2k divided by 5.99. This is equal to divided by negative 367.3. No? So if you compare the result, the answers, no? So this is for the bypass. So bypass. So with the capacitor, this is for the, these values are for unbypassed. So if you look at the input impedance of the unbypassed is greater compared to the bypass, you know, but the same output impedance, but the gain is very small, there is greater. So which do you think is best? No. So in amplifier, the greater the input impedance, much better. So the greater the input impedance of an amplifier, your amplifier has a better performance, no, compared to a smaller input impedance, no, amplifier. So that is why the voltage gain, but in order to have a higher input impedance, ang yung voltage gain is smaller. But in order to compensate the smaller voltage gain, so that's why we have a configuration which is cascade, where we cascade two transistors. The first stage will be the higher impedance stage, and the second stage will be a higher voltage gain stage to compensate the disadvantage of each other. So the first stage should be the higher impedance, and then the last stage should be a greater voltage, should have a greater voltage gain. So in order to compensate the disadvantage of both configuration. So this is for the unbypassed and the bypass capacitor. So like what I've said, the higher the input impedance, the amplifier can perform much better, no? So that's it for today.